Alright guys, well, just kidding earlier, I guess it's not the next concept yet. Concept 64 does include tangent graphs. Okay, on the bright side, these are not as tedious as the sine and cosine graphs. Okay, these are a lot more straightforward. Now what I want to start off first is recall that tangent theta, remember when we have our first identity way back in concept 53, you can look at it as sine theta over cosine theta. Okay, pause the video here, maybe take out your concept 53, I believe, and then you can review where this comes from. Okay, so here's the thing about tangent graphs. Okay, it says the tangent function is one of the trigonometric functions whose graphs have asymptotes. Graph the function below and show the asymptotes. Okay, so we want to show what the basic tangent theta will look like. Now, before you resort to your calculator and you start seeing what it looks like, okay? Now, just think, just like we were doing before when we were creating our table, let's take a few values for tangent theta, okay? So let's just take 0, okay? So tangent of 0 degrees, okay, would be sine of 0 over cosine of 0. So sine of 0, well, sine of 0 is 0, cosine of 0 is 1, 0 over 1 is just 0. Let's take tangent pi over 2. Now what happens here? Sine of pi over 2 over cosine pi over 2. What is the sine of pi over 2? The sine of pi over 2 is 1. The cosine of pi over 2, however, is 0. Okay, this is of course undefined. In other words, you can't have pi over 2. And if you recall from our current rational functions unit, okay, whenever you have something you can't input in because it gives you something undefined, you're gonna have an asymptote. Okay, so this one here, and yes, please draw out the asymptotes. Okay, would go there. Okay, and then it will work the exact same way. At negative pi over 2, you're gonna have an asymptote here. Okay, and then keep going. Let's do so. Notice that I have this gap here. So if I take pi, I mean, let's go ahead and take pi then. Okay, it doesn't hurt. So tangent of pi would be sine of pi over cosine of pi. Sine of pi is 0, cosine of pi is negative 1, 0 over negative 1 will be 0. Okay, so you'll be crossing here. And we also shown that tangent of 0 would be 0, so you're also crossing there, there, and there. What about 3 pi over 2? So tangent of 3 pi over 2, okay, would be sine of 3 pi over 2 over cosine of 3 pi over 2. So what is the sine of 3 pi over 2? The sine of 3 pi over 2 would be negative 1. The cosine of 3 pi over 2 would be 0. You got something dividing again by 0. So this one is also undefined. Okay, so you probably maybe picked up the pattern here. Okay, so there's an asymptote there. There's going to be also an asymptote here. Okay, so we have one there, 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 and there, and it would keep going infinitely. Okay, so then what does this look like? Okay, well, you can go ahead and plug in values for radian values for tangent, and you'll see that the value would keep increasing the closer you get to each asymptote towards the right side. However, the values you input getting closer to the asymptote to the left side is going to keep getting smaller and smaller, bit like huge. Okay, so just to take some values here to show you. Okay, here's pi over 2. Okay, so what happens when I take, for example, tangent of, let's take pi over 4. Okay, I get 1. Okay, so when I take pi over 4, I'm right at 1. Okay, let's get closer to the asymptote. Well, what would it mean getting closer, right? Well, I would have to take maybe, what, pi over 3. So if I take tangent pi over 3, I get 1.73. Okay, so I got closer, or something bigger. Okay, now let's get closer and closer to pi over 2. Let's take tangent of, say, pi over 2.5. I get 3.07. Okay, so it's going up. And then let's take tangent, let's take something even closer. Tangent of pi, right? So I'm getting closer to 2, right? So tangent of pi over 2 point, let's say 2.1. Okay, I'm getting 13.34. Let's take one more closer so you can see that it's just going to keep increasing infinitely the closer you get to 2.001. Okay, really close to 2. I get 1,273. So at one point it just shoots up. Okay, so the same way, okay, take going towards closer to the left asymptote. Okay, so if you take the negative of this, negative pi over 2.0001, and all these values here, you're going to get these values just negative. Okay, so what does this look like? What does this curve look like? Okay, it's actually going to look, well, we saw pi over 4 was 1, right? So we could plot that point there. Okay, it's going to look something like this. Okay, and this will hold true for every interval between each set of asymptotes. Okay, so this is what tangent looks like. Whoops, got sloppy there on my right one. Okay, and again, just same thing. For all sides. So there's that one. And then finally, okay, it would get cut off there. So that's what tangent looks like. Okay, so you could change the period and asymptotes here for the tangent. That's basically what changes. Okay, amplitude is undefined because it doesn't really have a max value. Okay, the period is, notice that from it's basically every asymptote, right? Pi over 2 minus pi over 2. What's the distance there? Pi over 2, it would be pi. Okay, so the standard tangent function has a period of pi. Given y is equal to a times tangent b theta, where theta is in radians, the period will be pi over absolute value of b. Okay, similar to the other one, except again it's not 2 pi, it's just pi now. And the asymptotes are odd. Okay, they're odd and multiples of pi over 2 times the absolute value of b. Okay, so with that said, let's look at the next one. Okay, so I have y is equal to 2 tangent theta. So looking at this here, okay, what changes here? My period, well, the a, okay, notice that the a doesn't really do anything. Okay, so my period stays the same, so I just have pi. Okay, so for my graph, what does that mean for my graph? Well, nothing really changes. Okay, your values, thanks to what would have been like an amplitude shift, it just makes them bigger, because for each tangent that you're going to plug in here, you're going to multiply by 2. So just like here when we were plotting right at pi over 4, I got 1. Instead, you're going to multiply by 2. So it just stretched the graphs within each asymptote. Okay, so what does that look like? Again, your asymptotes stay put. So draw those in, right? Those are my asymptotes. But again, you're stretching your values, or you're multiplying each of your values that you would have plugged into the standard function, instead this time by 2. So instead of having the, again, like, you know, the standard function, really, all you're doing is making things steeper because you're multiplying everything by 2. So it will look something like, you can plot the points at 2 because instead of at 1 you're going to be there. Okay, you're going to have something like this. right? And I don't know if it's easy to tell, right? I guess there's a more bendy section here in the standard function as opposed to here now. Okay, so have one there and there. And that's basically it. It gets cut off there. Okay, because of the, well, you still put your arrow because you know it keeps going. Okay, and there. Okay, so that's what number 1 looks like. For the next one, there is no stretch, right, or amplitude. Well, I don't want to say amplitude because that's not technically correct, but there's no stretch to the values here. It's just this one here. However, the period does change, right? My period, if I put 1/3 in here, I'm going to get 3 pi. Okay. Now notice that, at least from the standard function here, that my period was tied to where my asymptotes were, right? The negative pi over, or pi over 2 here, pi over 2 here, so a total of pi. Okay, the same thing is going to hold here. Okay, so I have 3 pi. So what is that? What is that going to do to my amplitude? What I want now, instead of just a pi distance between the asymptotes, I want 3 pi. Well, if I stretch from negative pi to pi, that would be 2 pi. So I have to go more. 3 pi over 2 and negative 3 pi over 2. So then these are my new asymptotes. Okay, and well, tangent of 0, you'll still get 0, right? So you're still crossing through the origin there. Okay, and you can just go ahead and what would be just a curve going really wide out as it goes towards both asymptotes, like that. Okay, and then you can go ahead and sketch what would be part of the others, right? So something like this. Okay, whoops, that's like one arrow there. There you go. Okay, so again, tangent graphs are a whole lot easier to work with. Okay, here, so my period does shift. Okay, so I have pi over, if I substitute this in for b, right, into my period value here, I'm going to get pi over 2. Okay, so what does this do now to my asymptotes, right? Well, normally it's a pi. There's a pi gap of distance in between. Well, now it's only pi over 2. Okay, so you're going to have more asymptotes in view, in other words. Okay, so what you just did is you cut that period, right, into a half. So this is normally what it is, right? It's from pi over 2 to here. So instead it's going to be from pi over 4 to pi over 4. Why? Because pi over 4 plus pi over 4 is pi over 2, the period. Okay, so instead, now, here are your, whoops, oh no, started doing that one wrong. Okay, ignore that one. Okay, this is what my asymptotes are now. Okay, and again, you're going to have a lot more in view now in this plane. You're going to have something like this. I always forget about the movie trivia, guys. I apologize. But I actually don't have anything right now in mind to give you guys. And then this is what tangent in this case would look like. It looks just like this. So you're going to have a lot more of these graphs present in this one. There you go. Okay, so that's number 3. For the next one, the last one here, I have 4 times tangent of 1/2 theta. Okay, so the period, I plug in half into the how my period is going to change, right? Pi over absolute value of b. I'm going to get a period of 2 pi. This one is almost similar to number 2. Okay, just one difference. Okay, this time there is a stretch of 4. Okay, so just like we stretched number 1 by 2, okay, make things a little more steeper or less bendy around the part where it crosses the x-axis. Something similar is going to happen. Okay, so let's go ahead and plot the asymptotes first. So normally, again, it's a pi distance. So then now instead is going to be 2 pi. So you're going to have asymptotes at pi and at negative pi. Okay, and then you're going to have another one going from pi. Well, actually, the next asymptote won't be in view, right? Because that would be a pi, and then you'd have to go more. Okay, so you're there. And then everything now gets stretched by 4. So when you plug in pi over 2, well, pi over 2, you're going to get, when we had it right, you're going to get, sorry, I lost my train of thought here. When you normally would plug in tangent pi over 2, you're going to get tangent pi over 4, and then tangent pi over 4, whatever that is, you're going to get times 4, so it's going to be a whole lot bigger. Okay, so instead of, I think, normally getting 1, right, because tangent pi over 4, sorry guys, it's late. Tangent pi over 4 is sine pi over 4 over cosine pi over 4, and then that is radical 2 over 2 over radical 2 over 2, which just is 1, but you're multiplying by 4. So you're going to get all the way up to here, and then you're going to get negative 4 similarly on the left side there. Okay, so then this tangent graph would go something like that. Okay, again, a lot, less bendy around the part where it crosses the origin here, okay, or the x-axis. And then similar, I think at 2 pi is going to cross here as well, and then you're going to have something, right, something similar going that way. Then at negative 2 pi, you have something similar coming up that way. Okay, that's it. That's all there is to tangent graphs. I believe these are easier than the sine and cosine, but that's not to say that sine and cosine were hard, right? Sine and cosine is just a matter of plugging in into a table and being able to get those values. Okay, all right, this time for real, until the next concept.